What's up, everybody? Welcome to lecture 8 of calculus. Today we're going to be going over section 2.1. Section 2.1 is going to pick up where 1.4 or 1.5, I can't remember which, we're going to pick up where that kind of left off. Because where that left off, we're talking about the secant line, and we're saying, all right, we know that we could write out the equation of the secant line, so a line that passes through some arbitrary function f of x through at least 2 points. And here we're going to call those 2 points a f of a, and a plus x, f of a plus x. And we could write the equation of the secant line as y minus y naught equal to m times x, the quantity, x minus x naught. So we could use point slope intercept form, right? And if we were to decide to set one of these values as a hardwired value and write the other point in terms of it, we could. So what I mean to say is, here you'll notice we used a, and then we went over some distance, delta x, right? There's no reason why we can't do that. We can always just say, hardwire some initial location, call it a f of a. And then go over some delta x in your x-axis and use that as your second point. So we're anchoring everything to this point. Okay. Now, from there, since we're anchoring everything to that point, it would make sense for us to go ahead and rewrite this slope, my mistake, this point slope form. It would make sense for us to write it in terms of that one anchored point. So let's set x naught equal to a, let's set y naught equal to f of a. From there, the slope of that thing, well, it's just going to be the difference in y divided by the difference in x, right? Okay. Well, question. What happens then if I let delta x get small? That is to say, what happens if I let this thing come inside? Move a little bit closer, right? So another way of saying that is what happens if we take this point and move it down? Well, eventually, as delta x gets smaller and smaller and smaller, or another way of saying that, as delta x tends towards 0, our secant line begins to start taking shape as the tangent line. Now what I mean by this is, we're taking this point and we're pulling it down, pulling it down, pulling it down, pulling it down, pulling it down. And as we do, it starts approaching this tangent line, right? And eventually, when you let delta x get to 0, you'll reach this tangent line. Okay, so this line over here, this tangent line that I keep talking about and kind of pointing off to, it's the line that is tangent to our function at the point a f of a. And since we anchored everything to a f of a, if we wanted to write the tangent line in terms of the point slope form, well, it would make sense to again use a as x naught and f of a as y naught. But that means then the slope has to be different, right? Because these two lines, these two lines in green, the secant line and the tangent line, they're definitely different. Those aren't the same lines at all. So something has to be different. And since x naught and y naught are the same, the only choice is for the slope to be different. So the question now is, what the hell is our slope here? What is that? How are we going to find that? Well, let's think back to what we did to get from there to over here. What we did was, we just set delta x to 0, right? Yeah, that's how we did it. We put this value get smaller and smaller and smaller and tend towards 0. Well, kind of like taking the limit, isn't it? In fact, it is. That's exactly what it is. It is taking the limit. So this slope here is going to be the limit as delta x approaches 0 of f of a plus delta x minus f of a, that quantity divided by delta x. And we can mark this off as the slope of the tangent line, and this over here as the slope of the secant line, if we want. Huh. Well, that's convenient, sort of. I mean, I have to apply the limit, but that's the only thing I changed here, was you're applying the limit. Okay, well, if that's the case, that means the slope is going to be pretty important, at least presumably, right? Because in that previous lecture that I referenced, as I had pointed out then, this tangent line and this function, when you zoom into that point A, FA, well, they become indistinguishable from one another. Meaning that this tangent line is important, and it's going to be useful in other applications, but it also means that that slope is probably going to be pretty important. Because it then turns out that since you can't tell the difference between the tangent line and the function at that point, or the points immediately around it, so for a very small collection of points around A, since you can't tell the difference between the two, doesn't that mean that your function at that point has the same slope as your tangent line at that point? And it does. That's exactly what it means. And for that reason, again, this idea of the slope of the tangent line becomes very important. So much so that we name it. And the first half of this class is entirely about this idea. It's called the derivative. And if you give me just a second, I will erase all of this and be right back to show you all more about the derivative and about this idea of the slope of the tangent line. We're going to use this limit definition and do a few things with it. All right, so starting off with a quick example, let's say we wanted to find the line that's tangent to the function x squared at the point 2, 4. How would we go about that? Well, we'd start off by saying, we know we could put that tangent line in point slope form. And if we do that, then what we're going to find is that y minus f of a is equal to the slope times the quantity x minus a. Well, we want this to be the tangent line, rather the line tangent to x squared at the point 2, 4. So doesn't that mean that a f of a is going to be equal to the point 2, 4? Yeah, absolutely. So already we know, just from this problem, that this is going to be the line y minus 4 is equal to the slope of your tangent line times x minus 2. So now, all we need to do is find the slope of the tangent line and then some basic algebra. So let's find that slope of the tangent line really quick. Find the slope of the tangent line. We know that m of t is going to be equal to the limit as delta x goes to 0 of f of a plus delta x minus f of a times delta x. All right, well we know that, or divided by delta x, I'm going to say. Well, we know here that a is equal to 2. So let's just write this out in that functional form and then kind of expand on it. So we've got the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 all divided by delta x. Well, we know that f of x is equal to x squared. So this tells us this all comes out to be the limit as delta x goes to 0 of 2 plus delta x, that quantity squared, minus, well, we know f of 2 is equal to 4, and all that divided by delta x. Well, we can expand this part out now, couldn't we? So let's do that. Expanding that part out, we get the limit as delta x goes to 0 of this 2 plus delta x, that quantity squared, when we expand it out, will come out to be 4 plus 2 times 2 delta x, or just 4 delta x, plus delta x, that quantity squared, minus all that, minus 4, and all that divided by delta x. Well, hey, check it out. When we drop these parentheses, this 4 and this 4 are going to cancel with each other. So all of this comes out to be the limit as delta x goes to 0 of 4 delta x plus delta x, that quantity squared, all divided by delta x. And now we get some more cancellations. Those delta x's are going to cancel out, right? Here, we can cancel out one of these 2 delta x's here, and this delta x here, with this delta x down here. To get that this is equal to the limit as delta x goes to 0 of 4 plus delta x. So that's just going to come out to be 4. So, we just found m of t, or my mistake, the m sub t, the slope of the tangent line, is equal to 4 here. We can come back over to our original equation that we wrote off in point slope form, put in 4, and do all the algebra that we need to do now. So this is going to come out to be y minus 4 is equal to the quantity 4 times x minus 2 and really quickly erasing this. Now, distributing this 4 all the way through, we're going to get that this is equal to y minus 4 equal to 4x. 4 times 2 is 8. Now, adding the 4 on this side to both sides, we get that y is equal to 4x minus 4. In other words, t of x, the equation for our tangent line, is equal to 4x minus 4. And that's it. That's all there really is to finding these tangent lines, using the limit definition. Having said that, let's keep carrying on. All right, now let's imagine I were to change that last example just a little bit. Let's imagine now that our function is x squared plus x, and I were to ask you to find a bunch of tangent lines. So just what I've got here, the line tangent to our function at the point 2,6, at the point 990, and at the point -3,6. Well, that's going to take a while, isn't it? It's not going to take a while because the algebra is bad. That was actually not that bad, right? It's going to take a while because finding each of those tangent lines is going to take a while. Or each of those slopes, rather, I should say. Because once you find the slope, it's just algebra. That's pretty quick. So wouldn't it be nice to have a generic formula to find the slope of a tangent line? Yeah, absolutely. Because then all you have to do, once you have that generic formula, is plug in 2, plug in 9, plug in -3, instead of applying this definition every time. This idea is called the derivative. The derivative is written, generally speaking, using the notation d dx of the function f of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all divided by delta x. Well, that doesn't look like it actually made the problem any easier, does it? But think about what this is telling you. Now, you don't have to go through this calculation for each tangent line. No. Instead, you just have to do this once and then plug in, like I said, 2, 9, and -3. And that'll be it. That'll give you each of the slopes. Which means this is actually a lot nicer way of going about solving these problems. And that's why we call it something special. We call it the derivative. And now, just to see how this is going to work, let's plug in our x squared plus x and see what happens here. So replacing all of this. What we've got is the limit as delta x goes to 0 of f of x plus delta x minus f of x all divided by delta x. Well, that's going to be equal to the limit as delta x goes to 0 of plugging in x plus delta x into this first function here, right? We've got x plus delta x, that quantity squared, plus x plus delta x, all of that minus x squared plus x because of the second function here, all divided by delta x. Okay, yeah, this looks terrifying, it looks disgusting, and it's going to be a bit of a drudge, I'm not gonna lie. But we're gonna get some reductions in a second here, and that's what's gonna make this worthwhile. Now check out this first part here. This first part is going to come out to be x squared plus 2x delta x plus delta x squared. Let's write that out. We've got the limit as delta x goes to 0 of x squared plus 2x delta x plus delta x squared plus x plus delta x minus x squared plus x all divided by delta x. Well, hold on. Wait a minute. We've got this x squared is going to be negative, right? When we drop those parentheses, and so is this x. So that means this thing's going to cancel, and this thing's going to cancel. So just really quickly, dropping those parentheses. We're going to get, like I said, this to cancel and that to cancel with this and with that. So this x squared is canceling with this x squared, and this x is canceling with that x. So what we're left with then is the limit as delta x goes to 0 of 2x delta x plus x squared plus another delta x all divided by delta x. Well, hold up. This means another cancellation. Because every term in your numerator has a delta x. You can just cancel those out with everything in the denominator. Since after all, everything in the denominator is just another delta x. So, that means you can get rid of this guy, kill that off, and get rid of that guy and that guy down below. To get that this is all equal to the limit as delta x goes to 0 of 2x plus delta x plus 1. But delta x is going to 0, and nothing else changes. So we're just going to be left with 2x plus 1. So all of this is to say that for each of the slopes of, for each tangent line, all you need to do to find their slopes is to plug in 2 into that equation down there, 9 into that equation down there, negative 3 into that equation down there. And oh my God, isn't that better than having to go through this process for each of those points? You only have to go through it once. So finding this general equation to derive the slope of each tangent line, so much easier, so much cleaner. Having said that, let's see if there's anything else we wanted to go over. Now before I wrap this lecture up, there's something I want to clarify a little bit. There are some other notations that will be used when talking about the derivative. So this is the typical way of writing it, right? D divided by dx of f of x. This is pretty typical, pretty standard. But other common forms of notation will be y primed, f primed of x, capital D sub x of f. This is generally seen insofar as I have seen it in engineering and some stuff in fluid mechanics, but that doesn't matter. Another common way of writing it will be dy dx and then df dx. Notice I'm not saying dy divided by dx. That's implied. That's because we're going to say dy dx, df dx, y prime, f prime so much until saying dy over dx versus dy dx, just getting rid of that over actually saves a lot of time. And it's pretty standard to say things like that, right? So just some common notation to be aware of. Having said that, final thoughts here. So there's this idea of differentiability. What differentiability is if you can apply this derivative to a function, it gives you something, then it's differentiable. The end. So if a function is differentiable at a particular value, let's say x equal to c, then that function has to be continuous at x equal to c. In other words, differentiability implies continuity, but continuity does not imply differentiability. And just to see that, there are a couple examples in the notes that I encourage you to look over. They show a few spots that are really common examples of where a function fails to be differentiable. One common example, I'll just draw on the board here, would be cusps. If a function has a cusp, it's just not differentiable there. So something like this. This function would fail to be differentiable right here, because it's a cusp. And if you think about the meaning of the derivative is talking about that tangent line, right? And the slope of that tangent line. Moreover, the slope of that function. But it uses a limit. So yet that limit has to hold from the left and from the right. Now, let's look at what happens from the left here. From the left here, this tangent line looks like it'll have a negative slope, right? My mistake, a positive slope. I meant to say a positive slope. Sorry about that. From the left, this tangent line should have a positive slope. However, coming at it from the right, so coming at it this way, our tangent line should have a negative slope. So at that cusp, our derivative just can't decide if our derivative, or if it should be a positive value or a negative value. Because the limit from the left and the limit from the right don't agree. So said simply, you don't have a derivative there. You just can't make up its mind what the value should be. So it wouldn't be differentiable at a cusp like that. That said, there are a few other examples. Like I said, they are included in the lecture notes that I posted online ago. With that being said, that is all I've got for y'all today, so I'll let y'all go. Have a good one, everybody.